Hi, I'm Joseph, and today we will be presenting our project, Eigenvalues Are All You Need, Reconstructing Faces from Voices Using Eigenfaces. And our mentor for this project was Abuzar Khan. So our brain is able to derive information of identity by hearing different voices. By hearing what someone sounds like, you could generally tell certain aspects of what they might look like, even if you haven't ever met them before. So it goes to reason that we could potentially build a system, an artificial intelligence, that could recreate the human face by only listening to a person's voice.
Hi, I'm Hanji. Let's talk about the dataset that we are using in this project. In this project, we use VGG Face and Voxelab. Both the datasets are being preprocessed by Wendy et al. We appreciate your tremendous effort. So for our model structure, there are three components. The first is a voice embedder. The second is a multilayer perceptron. And the third is an eigenface-to-face converter. For the voice embedder, its goal is to extract voice profiles from log mail spectrograms. And for the eigenface converter, it is responsible for converting the eigenface into facial images. Both components are produced without any prior knowledge of other components, meaning they're generated independently. And both components do not participate in backpropagation. Their weights are frozen in the actual training. So for the multilayer perceptron, it is the most essential components in the whole model. It transforms the voice profile to the eigenface, and it comprises of fully connected linear layers, batching norms, and Gaussian area linear units. When it comes to backpropagation, the loss is calculated on the eigenface and backpropagated from the voice profile to the voice embedder. So let's talk about the loss function. Recall that for each identity, there are multiple voice clips and multiple face images associated with an identity. So here comes the problem. It's a many-to-many mapping. For the loss calculation, a generated eigenface is compared with all ground truth eigenface from the same identity. And the loss is computed for each ground truth face, and we take the average. The loss function here we are using is a mean squared error function. So after the model structure, let's talk about how we use the dataset. In actual training, we actually have two sets of datasets extracted from VGG face and Voxelab. For eigenface generation, we sample face directly from the VGG face 2 dataset. There are 1916 identities selected and 10 image-per identity are selected for the eigenface generation. For the MLP training, recall that we need both the voice clips and the facial images, and there are only 1225 identities with both voice clips and face images. So we split them in 8 to 1 to 1 for the train test valid split.
Okay, hi, this is Adish, and I'll be going over the PCA and eigenfaces component of the project. So one of the novel contributions of this entire implementation was to basically reduce the dimensionality of the images that we are trying to project onto, and that could be done best by the PCA analysis and converting to eigenfaces. So what we've done is, as Hansi and Joseph explained in the dataset, we have 2,500 identities, out of which we've done an 80-20 split to convert into train and test data. And we've created 5,000 eigenfaces for representing the data. And as a proof of concept, what we wanted to first find is eigenfaces a good basis vector for representing images that it hasn't seen before. And that's how we started conducting our experiments. And the next part is for testing out whether our eigenfaces work on the test data set or not, right? So we have observed that for a large number of principal components, the eigenfaces is a good approximation. And as you can see in the two images on the ground truth faces and in the reconstructed faces, these are the faces that the algorithm hasn't seen before, but is able to
Hi, I'm Shreya. So I'll be going over how this entire thing finally stitches together. So these are the couple of faces that we generated through the voice input. And this I'll be going over what are the correct results and what are the wrong results we got. So first of all, we can see through the voice inputs, we were able to create faces with the correct facial features like jawline, cheeks, and facial structure. And it was followed through for a lot of inputs that we got. And our entire approach was able to recollect the facial features such as mustache and hair length. They were not able to completely be recreated because they don't have any correlation to the speech. So these are the few results that went wrong, because although, like I said earlier, some of the facial accessories are not there in the voice input, but our approach anyways were able to create the facial features. But while doing all of that, the model is generalizing the face a little too much, which is very close to the mean face. Hence, of the three faces that we have shown you for an example, they all look alike. So this is where we can improve further, and this is how we can conclude our work.
As Shreya was explaining, some of the other observations we made on what went wrong was the data set and the reconstructions are heavily dependent on the alignment of the faces, and the input data set that we've used to generate the eigenfaces are all front aligned. So if there is any change in alignment, that could not have been recreated, and The second part is the Amir Khan images that we see. There are some specific features in the face that could not be reconstructed. For example, the shape of the ears and the jawline. And it has reconstructed a face that is more closer to the mean face of the trained data set rather than the facial features of the specific person. So the model is lacking in completeness on some of those features, which may have a correlation to the speech, but yet could not be reconstructed.
So in conclusion, we were definitely able to show that eigenfaces can be used to create a generalizable method of representing any identity that might actually exist outside of the set used to make those eigenfaces, which is probably one of the biggest takeaways for the project. But we found that our model itself still suffers from a lot of the same issues that previous literature has suffered from, and that it has a lot of difficulty predicting some of the more distinctive features just from voice alone. It's usually able to discern more obvious things such as sex from voice, but it's not really able to determine a lot of the distinct facial features without actually having been exposed to very, very similar identities in the past. So a lot of our further research is going to go towards trying to figure out the reasoning behind some of these modes of failure, trying to figure out exactly where it lies, either in the model or in the voice embedding itself, and experimenting with a few different approaches to try to improve them. Thank you.